The Implementing Routing Facilities for Branch Offices lesson offered the opportunity to create and deploy an implementation plan for branch office connectivity under several related scenarios. In this debrief lesson, we will review our demonstration and try to reach some conclusions. What did we accomplish? We started configuring Internet connectivity with basic services, such as NAT, DHCP, and static routing. We then moved on to using the Internet connection as a backup to our private WAN. When the private WAN went down, we used an IPsec VPN across an Internet connection to reach the headquarters network. In moving forward in our migration plan to decommission the private WAN, we configured our IPsec VPN to run routing protocols, in our example EIGRP, and be able to eventually use both links with dynamic routing protocols to reach the private networks behind the headquarters router. In the end, if you look at our trace command to the LAN behind the headquarters router, sourced at the local area network in the branch, we are using the tunnel to reach the other side. We get there in one logical hop across the tunnel interfaces. The whole complexity of the public network is hidden, allowing us to use the low-cost connection for mission-critical traffic while protecting the traffic with an IPsec VPN tunnel. How did we accomplish this? If you look at our routing table, we learned about the 10.2.2.0 network via our tunnel interface. This is part of our GRE tunnel configuration. Let's display the final configuration of our Tunnel 0 interface. We have this IP address and IP subnet on the tunnel interface, which is nothing more than our point-to-point link to carry EIGRP advertisements. We sourced them at the loopback interfaces, which is why our tunnel sources and destinations match the loopback interfaces in our topology diagram. The reason we learned about the remote network via our tunnel interface is because our EIGRP routing protocol is using the tunnel interfaces as routable interfaces to send and receive EIGRP advertisements. Once traffic knows that it needs to go through the tunnel, the floating static route, displayed here, helps us reach the tunnel destination. The tunnel endpoint via this default route points to this Internet service provider. Remember, we used an administrative distance of 171 to make the static route trigger only upon failure of the EIGRP route. The default route was being advertised as an external network via EIGRP on the private WAN, with an administrative distance of 170. In forwarding packets toward the next hop, if we look at the routing table for the next hop, it's directly connected via our serial 0/0/0 interface. That is the interface that is attached to our crypto map, related to the IPsec VPN. Our show crypto map command was very useful in showing the interface where this was attached. That's how the EIGRP traffic is tunneled across GRE first, by going through the tunnel interface, and then via the IPsec tunnel through double encapsulation. This is the mechanism that allows us to run a routing protocol inside of the IPsec tunnel. Subsequent traffic, for instance our ping, will match the crypto ACL, also shown in the crypto map, and be encrypted and tunneled via IPsec. One of our conclusions was this traffic needs to be exempted from NAT translations. We accomplish this by changing the NAT configuration. If we look at the running configuration for the NAT statements, we can see that we are translating traffic according to this access list into the pool of public addresses. By changing the NAT-ACL access list, we were able to prevent VPN traffic from being translated, and therefore it matched the crypto-ACL and goes through the VPN tunnel. The final piece of configuration we can display is the NAT-ACL. Here's the deny statement, which prevents traffic going from 10.1.1.0 to 10.2.2.0 from being translated by our NAT feature. Some of the important lessons we learned are listed here. It's very important to identify and document existing branch router functions. They could not only have an impact on the IPsec VPN, but they could also be altered by the IPsec VPN. For instance, we need to tune NAT and prevent VPN traffic from being translated. We need to create NAT exemption rules. We also need to ensure that relevant traffic matches the crypto ACLs. We saw an interesting example of this in action when we could not trace across a tunnel because the return traffic was not matching the ACL at the headquarters router. Another important lesson is the use of loopback interfaces for stable GRE tunnel establishment, and also making sure the crypto ACLs match GRE traffic too. If not, the tunnel interfaces will not work, and the EIGRP will not be able to advertise through them. We could have implemented some alternative solutions to our deployment. For instance, backup interface commands allow you to accomplish a switchover to a backup link more quickly than relying on the EIGRP convergence in our example for the switchover to occur. We were bringing down the directly connected interface, but other failures in the network will rely on the routing protocol convergence in order to trigger the floating static route. With a backup command, you can trigger the backup by simply having the router identify link-level failures at the interface level. At that point, the backup interface is brought up and is ready to route traffic. In terms of routing EIGRP through IPsec VPN tunnels, virtual tunnel interfaces greatly simplify the configuration we created and provide a simpler alternative to using GRE tunnels for encapsulation and cryptomaps with IPsec. A major benefit associated with VTIs is the configuration does not require a static mapping of IPsec sessions to a physical interface. The IPsec tunnel endpoint is associated with an actual virtual interface. This is, then, a routable interface at the tunnel endpoint. Many common interface capabilities can be applied to the IPsec tunnel. They include the association of routing protocols, and therefore routing across the IPsec tunnel. In the end, VTIs are a good alternative to IPsec over GRE tunnels. Looking ahead, it is common for dual head-end routers to be used for redundancy in larger networks. As you look at the diagram illustrating this, think of the implications in terms of a full mesh of GRE tunnels if hub-to-spoke and spoke-to-spoke traffic flows are required. And they will be. In today's branch scenarios with voice-over IP calls using the WAN for voice services, you will probably require spoke-to-spoke connectivity. Again, imagine configuring a point-to-point GRE tunnel like the one we created for this environment, in which you require a full mesh of tunnels. At that point, the number of IPsec and GRE tunnels per interface will not scale. You need solutions that are more effective. Enter the Dynamic Multipoint Virtual Private Network, DMVPN, and the Group Encrypted Transport VPN, GetVPN. They combine multi-point GRE tunnels, dynamic resolution of endpoints, and crypto profiles that override the requirement for defining crypto maps. In preparation for more complex scenarios, you may want to research these technologies and gear your preparation toward these topics. This signals the end of a series of lessons related to routing facilities for branch office scenarios. We will move on to another series of lessons related to routing facilities for mobile workers.